Okay. Good morning, good evening, good afternoon. I'm Stefan Brudzinski, the EUMETSAT third generation user preparation project manager at the EUMETSAT, and I'd like to welcome you wholeheartedly to this event. We have 150 registered participants, so we are quite excited to have this event today and tomorrow. This user preparation webinar on the next generation hyperspectral infrared sounders that are to be launched and operated by EUMETSAT in this decade is geared towards raising awareness of the users of these exciting new missions. There will be a lot of innovation coming from both missions and a lot of heritage that we can build upon in having used hyperspectral infrared soundings in meteorology and atmospheric composition. The two instruments are the infrared sounder, IRS, on the EUMETSAT third generation sounding satellite, MTG, which is to be launched in 2023, and the infrared atmospheric sounding interferometer, new generation, IASI-NG, to be launched on the METOPS second generation A satellite, also in 2023. We organized this webinar as a first in this series on the observation missions of MTG and METOPS second generation. So there will be other webinars on the other observation missions in the coming months. Today we focus on the instruments, the scanning principles and the measurements at the radius level, the basics of data format and dissemination. And tomorrow we'll have focus on the geophysical products and some application examples in meteorology and atmospheric composition. You can see the agenda here flipping through in the screen that is shared. So with these webinars, we want to trigger developments in the development of processing and visualization software and algorithm development, and stimulate development of applications. So please, if you have any questions regarding these presentations today and tomorrow, please use the Slido tool, www.slido.com, and use the event code NG-HSIR. I repeat, NG-HSIR, which stands for Next Generation Hyperspectral Infrared Sounding. It's also visible here in the Zoom group chat that Rosa is maintaining for us. So please ask your questions there, and we'll try to answer them during these sessions or offline later. We'll make the recording of today and tomorrow available, as well as the presentations afterwards. During the session, please keep your microphone muted and your videos off to save bandwidth. And with this introduction, I'd like to hand over to our first speaker, who is Dorothee Coppens from EUMETSAT. Dorothee, the floor is yours.
Okay, thank you. Hello everyone. I have the pleasure to start this presentation. I have to share my screen first, sorry. To start this webinar with a presentation of the new missions, and I will focus on the instrument and the associated calibration. Okay, so I don't know if you all see my presentation. So I will present IASI-NG and MTG IRS instruments. So first of all, we are preparing at EUMETSAT the future hyperspectral infrared instruments, and those instruments will be flying on two types of satellites. The first one is on a polar orbit satellite, which is a synchronous orbit and at an altitude of about 800 kilometers, to provide detailed observations of the global atmosphere, oceans, and continents. So currently we have already the EPS, the EUMETSAT Polar System program, with the 3 flying instruments. And on the METOP satellite, which operates in unison as long as we have METOP A available for sure. And we're preparing the future EPS second generation program with the new IASI new generation instrument on the 3 satellites from 2023 onwards. Then we will have hyperspectral sounder on the geostationary orbit. So this mission is called the EUMETSAT third generation, that will include the state-of-the-art atmospheric sounding service, providing measurements in the infrared spectrum. MTG will see the launch of 6 new geostationary satellites from 2022 onwards. And we will have 4 imaging satellites and 2 sounding satellites. And the MTG infrared sounder will be flying on the 2 sounding satellites. The outline of this presentation is quite simple. I will have a short reminder on the current IASI mission. And then I will present you the 2 new missions in comparison with the current mission that I think everybody knows. And I will conclude on the possible synergies and also have a quick look to the level 2 product. So first reminder on the IASI mission. So the IASI is a Michelson interferometer flying on the METOP satellite. It's scanning the Earth over a swath of more than 2,000 kilometers across track scanning. You have at the top right the characteristic of the instrument, the spectral characteristics with a maximum OPD. This is an acronym you will see in many slides. It stands for optical path difference. That is linked to the spectral sampling and spectral resolution. IASI is providing continuous spectrum from 645 to 2,760 centimeter minus 1 with a spectral accuracy better than 2 ppm. The radiometric characteristic is the noise is less than 0.5 Kelvin. And you have also the geometric characteristics with a field of view. So the pixel size at nadir is 12 kilometers. Each detector matrix is done by a 2 by 2 pixel, covering 50 by 50 kilometers by kilometer. So currently we are flying 3 METOP, and you have here the launch date of the three instruments. Main characteristic to retain, to remember is here you have the comparison between the IASI in black compared to the spectral coverage of the other hyperspectral sounders, and you see that IASI is covering the whole range of channels, and with a very fine spectral sampling of 0.25 centimeter minus 1. A very important characteristic for IASI is the accurate radiometric and spectral calibration, which give a very good stability in the data quality across the 3 instruments. And I present here 2 types of comparison. On the left, the two plots you see on the left are the annual interpixel stability, and you see that for IASI A and B, they are within 0.1 K, which is a very good accuracy. And on the right, you see for 1 month, as an example, the comparison between the 2 IASI, IASI C and IASI B, where you see also that this is within the 0.1 K as well. So it really shows a very good quality and accuracy of the instrument and on the calibration. So now I will go to IASI-NG, and the way I will present it will be the same also for MTG IRS. Here I give the characteristic of the instrument, and I have highlighted in orange what is the improved characteristic compared to IASI, or the new characteristic, let's say. So IASI-NG so is a continuation, of course, of the IASI instrument. So it's still a Michelson interferometer, but on top, the instrument has a MERX compensation. I will explain later what it means. We have also still the same spectral coverage. On board, we have a multiple laser beam, which is an improvement compared to IASI, and it allows us to have a better and more accurate monitoring of the corner cube movement of the interferometer. Spectral sampling is twice better, and the resolution as well compared to IASI. The swath remains the same, and the pixel size is still 12 kilometers. The detector, 4 by 4 kilometers compared to IASI. So the IASI was 2 by 2. So the coverage of each sampling is larger. And also IASI-NG will have half of the noise of IASI, so that will be 0.25K. So improved technology of the instrument for IASI-NG, what does it mean? The Michelson, so it's a Michelson interferometer with a MERX compensation. So it means that on board, it's by hardware, there's already a compensation made at the instrument level, compensating of the field of view of the different pixels. And that has a very good effect on the spectral calibration, and that I will explain it when I show you the processing. We will have 4 bands compared to 3 bands, and that allows us to reduce the noise, especially in short waves. The improved metrology of the instrument allows us to carefully and accurately monitor the corner cube movements, and that's also give a better quality of data. And the max optical path difference of 4 centimeters, this characteristic is the size of, it means that it's the size of the interferograms, and that gives us the finer spectral sampling of 0.125 centimeter minus 1, and with a spectral precision of 1 ppm. For information, IASI-NG also will contain integrated imager, so co-registration will be made with MetImage, and the cloud information will also be available in the product. So I show you very quickly here, because then you will see it in another presentation today. The geometric characteristic of the IASI-NG, with you see on the left the pixel, each scan view will scan 14 pixels instead of 4, and then each field of view, which is a pixel, is 12 kilometers at nadir. So then here you have roughly what IASI-NG will cover at each line with this 14 scan view. But that will be explained later by my colleague. And at last, for IASI-NG, what is the effect on the calibration? Here I show you the main sequence on the calibration process. And I put IASI as a reference, then at least you can see the improvement we have made with IASI-NG. Improvement, but also we needed to adapt the processing to fulfill the new characteristic of the instrument. I've highlighted in green what is linked to spectral calibration, and you can see that this MERX compensation of the instrument has already an effect of reducing drastically the spectral shift. So it's a kind of a first spectral calibration that you have on board at instrument level. And also in terms of particularities, you have a spike detection, but for IASI-NG, we will have also a correction of those spikes. And on ground processing, the difference with IASI that we will downlink the interferogram, so that's give us opportunities to do a very accurate monitoring. The radiometric calibration will also be done on ground and also will be done in different manner, because then we can also monitor that very carefully. We optimized the calibration sequence in performing the spectral calibration first, and that is an improvement. And on top, for the user, there will be, like before, spectral uniformization, meaning that you will have one standard spectral response function to use on the user side. MTG IRS, I will have the same way to present it. So first of all, the instrument is one of the two instruments which will fly on the MTG sounders, developed by OHB in Germany and Thales in France. And so it means providing high spatial and high temporal information of the atmospheric temperature and moisture structures. The main targeted users are the nowcasting user community and numerical weather prediction users. There are never been any operational hyperspectral sounder in GEO. The only one flying right now is the GEARS from China, flying on the A54A, but is still not an operational instrument. So IRS will capitalize on this 20 years of experience of operating the infrared hyperspectral sounders from the LEO satellite, and also we are taking some feedback, and we are learning also with the GEARS instrument currently. So here also I put in orange the differences between with IASI. So the MTG IRS is an imaging FTS based on the Michelson interferometer. Corner cube mechanism is similar to the one of IASI. Multiple laser beam LAC4 IASI-NG is present in the instrument for monitoring carefully the movement of the corner cube. The max SPD is smaller, which provide a sampling slightly larger than IASI and IASI-NG. But the detector array is very big because it's 160 by 160 pixels every 10 seconds with a spatial resolution of 4 kilometers. We won't have a continuous spectra. So here you have the two bands, and we have also extended spectral range that is written in this slide. So MTG IRS is also a step forward compared to IASI with this new technology, but most of it is because of this larger field and better spatial resolution and higher temporal repetition. And of course, we will have an additional user community, the nowcasting people. So different instrument, of course, you will see that there's also different calibration methods. But first of all, I will show you, as I've done for IASI-NG, the scanning sequence. So the Earth disk is split into local area coverage zones, and each of them covered 50 minutes by a succession of steps and stairs called dwells. So here you have the LAC 4, 3, 2, and 1. And the LAC 4, it will be covered every 30 minutes, and the LAC 1, 2, 3 will be alternatively viewed in between. But this will be explained by my colleague as well. For each, in each LAC, you have what we call the dwells, and the dwells are the scan view of 160 by 160 pixels. Each pixels, you will have 2 interferograms that will give a full calibrated spectrum at the end. In terms of processing, so here also I make the comparison with IASI because it's the one we know and we are operating currently. So you have a complex metrology that I explained already before. There will be an inversion of the interferogram direction. Also, it's an improvement. It has never been done before. There's, like IASI-NG, there will be a spike correction. And also like IASI-NG, but in different way, there will be a field compensation, not hardware, but this time it will be software. And there's also a decimation, which means that we also compress the signal before downlinking it. And then on ground, we have also a new calibration, spectral calibration methodology. And here also I put in green what is linked to spectral calibration. So the field compensation on board is also doing part of the job. And we will have also a spectral uniformization, so which means that a unique standard spectral response function will be made available for the users. We will have spectral calibration done before spectral sampling calibration this time, like we have done for IASI, and also for at the IRS we need to perform a stray-like correction. There won't be any strong apodization, but this could be done as a post-processing, the post-processing which is called the IRS PP. Just a very quick reminder of what are the different characteristics for all three instruments in terms of spectral information. So you see here in green the number of spectra you have per line and per dwell for the MTG, the size covered in red, and the number of channels you will have for each instrument. But all this information will be provided by my colleague Bertrand Théodore today when he will talk about the product format and dissemination. Of course, because of the huge amount of spectral channels that we will have, and also the huge amount of data we will have, we are already doing that for IASI, but we are compressing the spectral information into principal components. But something which is very important is for the IRS, as you can understand, with the number of spectrum you will get every 10 seconds, so 25,600 spectra every 10 seconds, we need really to compress the information. And that will be, so the principal component scores will be the only product disseminated to the users. I will not go really into detail here because I'm not the expert here, but you will hear about it later today. So, in summary, all the spectral information is projected in some main directions, and that allows us to, for example, for IASI to give the same information. We have the 8,000 channels that will, well, the content will be done in 300 PCs, and then after you can, from the PC, you can reconstruct radiances. But I don't go into detail. The only thing I want to mention here is that different methodology has been applied. For IASI, we had what we call the global PCs, but for the future mission, and then will be also done for IASI and IASI-NG, we have proposed what we call the hybrid approach to supplement these global PCs with 5 local PCs to capture possible outliers. But this will be presented by my colleague Tim Albert today, so he will explain about the PC methodology, but most important, how to use them. So I will conclude with 2 main things. First of all, I would like to show you, at least to remind you how complementary and the future mission will be between the EPS-SG and MTG. So, and to look at and to think about possible synergy. So here in this slide, we represent the IASI and IASI-NG pixel that you have in the black cycles. And so here it is for IASI, but there will be the same kind of pattern or coverage for IASI-NG, something that you have in the end over Europe around 40 kilometers resolution, and it's twice per day. And then on top of it, you could have the IRS pixels of 7 kilometers, continuous pixels, and this information, so it's like an image that you have on top. And this information will be provided every half an hour. So you have at the bottom the path when you get those data. So you have twice a day. If you have 2 or 3 IASI-NG instruments, then you have 6 times a day. But if you want to combine with the IRS, then the IRS, being every half an hour, can really complement the data you are receiving and for your applications. So that was the first point of my conclusion, not to forget that. The second one is just, I will take to show you the advantage of the advanced technology and the accurate redundancy when you want to look at level 2 products. I could have showed you one for IASI-NG and one for MTG IRS. For MTG IRS is quite, in a way, is quite obvious because the mission characteristic is so different that, and with this synergy, you really see the advantage of having a data measurement every half an hour with a pixel resolution of 4 kilometers. That really is bringing like something new to your applications. So I decided to focus on IASI-NG compared to IASI, and to show one example that I had, but it's so here on the left you see a spectrum, IASI-NG and IASI. So where you see that IASI-NG, the absorption line are really deeper, and so they are better described compared to IASI, and that will give at the level 2. If you look here, you have the Jacobians representing, it's a vertical Jacobians and horizontal Jacobians, and you see that for the vertical, that really it shows that with IASI-NG is more sensitive and vertically higher resolved, and also for the horizontal Jacobians, it's an example of the CO2, shows really that IASI-NG is much more sensitive with a higher rank than with IASI. And with this, oh yes, of course, I forgot that. Of course, this aspect will be largely explained or shown by my colleague Thomas Auguste, and also with Pierre Coher from ULB. So that's those two presentations will be tomorrow. And with this, I thank you for your attention.
Thanks very much, Dorothy. Great talk. Thanks. And I invite questions from the audience. We have, as I said, slido.com and event code NG-HSIR. Please ask your questions there. So we have, perhaps Rosa, we can show the questions. We have one first question, which is the following. What is the reasoning behind keeping the pixel size the same for IASI-NG at 12 kilometers? Why not better?
Yes, when we were defining the mission, we wanted to have a better spectral resolution, having a better noise, and having a smaller pixels. But in terms of technology, that was too much for industry. And so after a lot of discussion within the IASI Science Working Group, we have decided to keep the better spectral resolution and reduced noise, and then keep the 12 kilometers. We couldn't have the 3 improvement, let's say. But with MTG IRS, then you have the complementary, because there will be 4 kilometer pixel. And so that's why those 2 missions are very, very complementary.
Okay, great. Is the spectral response function uniform?
Yes, okay. The spectral response function uniformization, the main purpose of this is to have one response function for all pixels, so for all dwells, and the same in the lifetime, and only one will be used, and the same for all spectral channels. So that is exactly the same way we are doing that for IASI. That will not have any change in the spectral resolution in time and yeah, spectrally and geographically. Only one. which means that the instrument feature will be removed. Instrument dependency will be removed in the level 1 processing.
Okay, one question here.
I don't know. Yeah.
Do you provide the IASI-NG data as principal components only, like for IRS? And I wanted to add to this, you said that the data will be available in principal components format only. That applies to the near real-time data, which is of course where the highest value of the data lies. My understanding is that the spectra will be available from the data store archive later.
Yes,
for users.
so the first question is no, we don't provide the PC only for IASI-NG. There will be radiances, but the PC are also available, like for IASI. For the IASI, you have the possibility to have the radiances and the PC, and that will be the same for IASI-NG. It's only MTG IRS where there will be only PC. But in the archive, I guess all product will be available. It's only for near real-time dissemination.
I think we have time for more questions. There's one question here about apodization. You mentioned the apodization approach for IRS.
Yeah.
Is the apodization for IASI-NG the same as for IASI?
Yes, we do the same apodization for IASI-NG than for IASI. I mean, of course, the resolution is twice better, so but it's twice higher. So then, but it will be exactly the same apodization, Gaussian function.
There's a question here on visualization and software, processing software. Is that available or being developed for IRS and IASI-NG level 1 data?
That's a little bit outside of what we are doing in my team, but so it's more like for maybe on the USC side. We can answer this question for the users.
Yeah, I believe there is in the NWP satellite application facility, there are efforts to develop such processing software.
Yeah.
And we can refer to those plans in answering that question.
Yes, I mean, if it was done for IASI, it could be done for the future instrument as well, definitely.
What is the field compensation correction is a question here.
Okay, so the field compensation correction, it depends on which instrument you're talking about. Because the field compensation is made differently, it's made in hardware for IASI-NG and in software for MTG IRS. So for IASI-NG, the field is compensated by the MERX compensation, which is, you have like two very thick prisms which are moving to relocate in a way all pixels as they were at the center. So that is hardware, it's made hardware. And because the spectral calibration, the spectral shift is induced by the position of the pixel further away from the center. The furthest away you are, the bigger shift you get. So then with these two prisms and movement, they managed to put all pixels like they were measured at the center. So that is for IASI-NG. And for MTG IRS is software. So then what they do is that they're resampling all interferogram measured in the field of view. On the field of regard, on the dwell, they resample all interferogram as they were sampled at the middle of the field. So it's done by software in resampling the interferograms. I don't know.
So when you say in the middle of the field for an IRS dwell, that means in the middle of each dwell?
No, it means on the interferometric axis.
Okay.
which is normally in the middle of each 12, but the interferometric axis is not always in the middle of the detection matrix, but which it should be, but also this shift, I mean, this difference needs to be corrected on ground afterwards, for example. But what it means is that every interferogram are resampled on the interferometric axis line. And that's a way we can remove a big part of the spectral shift.
That's great. Okay, very good. Thank you very much, Dorothy. It's time to move on. We have more questions, but we'll answer them either in the later Q&As or after this event. Before I move on to our next speaker, I'd like to remind you all, 138 participants, that we have after this webinar a very small poll with 5 questions, and we'd like you to give us an answer and your opinion about this webinar, because this is also something new to EUMETSAT, to organize user preparation webinars in the absence of face-to-face meetings in the current situation. So please take 2 minutes to answer those poll questions at the end of this event. They will help us improve the webinars. So with that, I'd like to give the floor now to my colleague Bertrand Théodore, who will speak to us about the details of the data formats in which the data will be made available and the dissemination baseline. So Bertrand.
Thank you. I'm here. Yeah. Good afternoon, everyone. The video will be. So I'd like to say a few words about the IRS and IASI-NG product format and dissemination. It's quite a dry subject. I don't have many nice images, but I want to give you an overview of what you will get if you want to use this product. So first, let's talk about IASI-NG. If you are familiar with IASI, maybe you won't be that much surprised about IASI-NG. As explained already by Dorothée, IASI-NG is a cross-scan instrument. So you will have 14 field of regards across the track, and each field of regards, FOR, is 3 by 3 degrees, containing 4 by 4 field of view or pixels. One pixel is 12 kilometers, and the distance between pixels is 24 kilometers. So it's very similar to IASI. One line contains 14 field of view and some views for the calibration. One swath is 2,000 kilometers, and one line lasts about 8 seconds. 15 seconds, sorry. So what will you get as a product? There is 2 level 1 product, as already mentioned by Dorothée. There is the radiance direct, so the spectra, for which the size is about 5 giga per orbit in NetCDF and 4 giga in buffer. You will have, of course, half of the product by day, half of the product by night, and the product will be distributed on EUMETCAST, and there is also a regional dissemination. The second product, to be able to cope with the size of this data, is the IASI level 1 principal component compressed product. And you see on that table that the size of the NetCDF file is very much reduced because it's only 253 megabytes. And otherwise, it has the same characteristics than the IASI 1C product, full radiance. All the other products that will be disseminated are level 2. So we will have a product for the water vapor, surface properties, cloud, and product for the atmospheric composition. All products are archived in NetCDF4 and are distributed either in NetCDF4 or buffer, depending on the channel that you are on which you are receiving them. It can be EUMETCAT or GTS or even offline retrieval from the archive. The size per day is 14 times the size of one product by orbit. So, for instance, for the product principal component product, it is about 3.5 gigabytes in NetCDF. So I don't give any insight of the scientific content of the product. To do that, please refer to the presentation by Tim Mulberg just after me for the product for the principal component, and for the level 2 to the presentation by Thomas Auguste tomorrow. So about the timeliness, so for IASI-NG, the timeliness is made of several components. The main one for low Earth orbit is the time that the satellite needs to reach the station to dump the data. So this is the onboard latency. Then, of course, you need time to downlink the data from Svalbard or McMurdo, or you need the time to process the data, level 1, and then level 2, of course. So what does it give for METOP-SG? So in fact, we will focus only on IASI-NG. So for level 1, you see on this table the percentage of chunks of piece of data, if you want, that will be available after 55 minutes. And you see that the level 1 will be available after 57% of the chunks will be available before 55 minutes. And all the data will be processed within 64 minutes for level 1C and level 1D. So full radiance or principal component. For level 2, all product will be available within 4,000 seconds after the acquisition, that is 73 minutes. Of course, IASI-NG product will be available also from regional station. But you don't have access to the full globe, of course. From a regional station, you have access only to the data acquired above when the satellite is in the vicinity of one of these stations. And the list of stations is here on the right. There are 8 of them in the Northern Hemisphere, mostly over Europe. And you see on the top right the coverage of this station. And the data volume of this product is about 9% of the volume of the size of the global product. So here, this is an example of the content of the file that you will receive. So it's a NetCDF file. I didn't put all the group, all the variables that are in the product. It's just to give you an example. It's simply done with H5dump, so it's really simple to have access to that. There is no complicated binary to read. And you have, of course, for example, the geolocation, radiance classification. So if the pixel is cloudy, clear, land or sea, and of course the spectrum and the wave number for the level 1. And level 2, you have the same information, geolocation and the status of the satellite, and for example, the air pressure at the top of the cloud, the air temperature, and the geophysical variables. So what about IRS? So IRS will be something completely new and very maybe complicated to use because of the volume of data. So Dorothée already told you about the IRS scanning sequence. I just recall it here. So the full disk will be divided into 4 zones of interest, which we call LAC. The LAC 4 corresponds to the northern mid-latitude that will be covered every 30 minutes. And the other LACs, the other region of interest, will be viewed in between. On the right here, you have, as a function of time, which lag will be imaged at which time. So one lag is covered in 15 minutes. So you see that the lag 4 is covered every 30 minutes and the other in between. This is the coverage of lag 4, lag 3, lag 2, lag 1, and everything. The dwells, so the field of view that is outside the Earth correspond to the calibration views. So one dwell consists of 160 by 160 pixels, which dimension is about 4 kilometers at nadir, and a bit more, of course, at mid-latitude, about 8 kilometers. Each of these pixels gives an interferogram, in fact, 2 interferograms for the 2 bands, the 2 spectral bands, and each interferogram gives 2 spectrum, and each spectrum gives a profile, a level 2 profile. So in fact, you will get one dwell is imaged in 10 seconds, so every 10 seconds, you will get 25,600 spectrum and as much as level 2 profiles. So this is, again, how the IRS will see the Earth disk. So again, you recognize the dwell over the 4 lags. The dwells are numbered from 1 to 280. There are 280 views from the South Pole to the North Pole. So there will be several level 1 products that are in the table here. In fact, it's not a product. Each dwell will be one product, but one they will share the same name for depending on the lag that they belong to. So the distribution, the generation periodicity is 15 minutes because the time to cover one dwell is 15 minutes. There will be one lag product per lag, and what is distributed is the principal component. The full spectra will be archived, will be available from the archive, but not distributed directly because of the size. Because yes, I have the level 2. Before talking about the size, level 2 product, there will be again one product per lag, divided into chunks. Again, one chunk corresponding to one dwell, and then 25,000 profiles. In each product, you will have temperature, humidity, and ozone profile, surface parameter, cloud products. The resolution is again 4 kilometers, of course, and they will be available with a generation periodicity of 120 minutes, whatever the channel, the distribution channel. The size of the product, as you can see here in the 1, 2, 3, 4, 5, 6, 7, 8 column, the full spectral sounding is 7 giga per lag. But using the principal component, we are able to reduce this size to 1 gigabyte. So this is why we distribute only the principal components. The format, again, is netcdf4, so it's quite easy to read. In this table, the peak periodicity is the time required for the product to be disseminated, and the big data rate corresponds to the worst case, that is the product size divided by the timeliness. So talking about the timing, this is the same for level 2. The size of the product is 2 giga per lag, and the average daily rate is 2.4 megabytes per second. And there will be one product per dwell, and with per lag. The timeliness for the level 1 is 900 seconds. So the product will be available 900 seconds after the acquisition, with a daily volume of 13 giga for lag 1 and lag 2, and 26 and 52 for the lag 3 and lag 4. For the level 2, the product will be available 1,800 seconds after the acquisition, with a daily volume of about 26 gigabytes for lag 1 and 2, and 52 for lag 3 and 4. So this is again an example of the product content from NetCDF4 file. So there is nothing surprising. Again, the dwell colon row, down fraction, latitude, longitude. And sorry, in that case, for the principal component, the PC scores and the local PC scores, because we use the hybrid method to distribute the data, to compress the data, and of course the geolocation, the satellite as the viewing angle and the position of the satellite. And with that, I will finish here with a view animation of how the IRS will view the Earth disk. Thank you.
Thank you, Bertrand. There's certainly a lot of data to come, and I hope this presentation gave you some details. There are various data services that EUMETSAT provides, through which you can receive the data. There is EUMETCAST satellite, EUMETCAST terrestrial, and there will be an online data store access for offline access to the various data types here. We are looking at the questions. Yeah, so there is a comment from Sally One-Up that near real-time data from the next generation satellites will be made available via the EUMETCAST satellite or terrestrial services, depending on the decision by member states to assign priority to the various data streams and or offline through the data store.
Yep.
For IASI-NG level 1 full spectral near real-time data dissemination is planned via EUMETCAST terrestrial, which is basically through terrestrial lines using national research networks or commercial internet. Yep. Okay, let's see what we have. There is a question here about, go slow down. Can you scroll down? What was that? Further down. These are questions still related to the previous presentation. I think we can also take them.
I started to answer them online, so.
Oh, you do? Okay.
Yes, that's because I thought it was related to my previous presentation, so I start to reply them online. I don't know if it was.
Yeah, please go ahead with that.
So.
Go ahead with that.
Sorry.
Will the MTG, so take the first one here. Will the MTG IRS spectra, I assume that's what's meant here, be available for the limb use?
That's a good question. Yes, in fact, there will be measurements at the limb for the calibration. So there will be, yes, data taken at the limb, and distributed. And
very high slanted view.
So of course, level 1 will be available. I'm not sure that the level 2 will be able to cope with this acquisition, but the level 1, yes, the spectra will be available.
And also very high slanted view also will be available.
Can you repeat what you just said, Dorothée?
I said, no, but because Bertrand said it's true for the calibration view, but also very high slanted views will be available as well. That will be available, and also for the level 2, we're working on it actually, to have it for the level 2 as well. But for the spectra, that will be available for sure.
Good. There is a question about, if you scroll down, whether the selected channel subset go down.
Yeah.
So there's a question about the dissemination of a subset of channels of IASI-NG, I presume, for NWP purposes, like 500 channels.
Yeah, for the GTS, yes, we are working on that to have a selection for IASI-NG. This is ongoing, but it's yeah, that's foreseen. Yeah.
Mm-hmm.
But we're working on that with the IASI Science Working Group to have an optimized selection. Yeah.
Okay.
Mm-hmm.
Perhaps we can take the next one since it's there. It's not directly related to Bertrand's, but we can still take it. Do you confirm that the 1,960 channels is the final choice of available channels from IRS?
Yes.
I presume the answer is yes. Yep.
For sure, yes.
Yes, it's linked to the instrument anyway. So, and the instrument is being built and defined. So, yeah, that's confirmed.
The ones on the PCs, I suggest we take them after Tim's presentation.
Yes, good idea.
That's what I answered. I said, see Tim's presentation first. Yeah, exactly.
Which line-by-line model are you using to compute the Jacobians? Is there?
For the slides I've showed, it's not a line-by-line model, but I think that will be answered and tomorrow with the level 2 presentation. So I think you should wait for tomorrow's presentation to talk about that. It's coming from the level 2. So
what else do we have?
For the reconstruct principal components, I answered that it will be good after Tim's presentation.
Yes, there is a question here about direct reception, direct readout data.
Yes.
Will this be done in a similar way as to the current dissemination from METOP?
Yeah, that's
yes,
exactly. It's very similar. Yeah, exactly.
Okay. Okay, in that case, if there are no more questions, I suggest...
I have answered the last one, and that the PC scores are computed on the calibrated radiances. So it's done on ground at the end of the processing. For the next one. For that one, yeah, sorry.
It's part of the ground processor.
It's at the end. It's done after calibrated radiances. So it's really at the end of the processing.
Okay, good. Okay, then let's move on to our next speaker, which is Tim Hultberg from EUMETSAT, who will talk to us. Hi, Tim. Hey. Good afternoon. Who will talk to us about the details of the principal components. So please share your presentation.
Yes, do you see it?
Yes.
Oh.
Just make it full presentation mode.
It's not. It's better now.
Very good. Good to go.
Okay, welcome to this presentation about compression. So as you just heard, the future hyperspectral infrared sounders will produce a huge amount of data. So there is, of course, a strong interest to compress the data before they are disseminated to the users. But compression is not only useful for dissemination, Also, for the vast majority of applications, the data must be presented to the algorithms in a compressed form in order to use them efficiently. And now I would like to end my video. Yeah, so the principal component compression works by representing the radiance data in a lower dimensional space, which is spanned by the leading eigenvectors of the noise normalized data covariance matrix. So this lower dimensional space we refer to as the signal space. And the reason we can represent the data in such a low space is that the radiance data are highly spectrally correlated. This is why we can remove the part of the data which is orthogonal to the signal space. So we can say that the high compression rate that we achieve really relies on the abilities to suppress most of the random instrument noise from the measurement. This is in contrast to lossless compression, where by definition we want to preserve the noise, and since the random noise cannot really be compressed, we cannot overall retrieve very good compression rates. So this slide gives an overview of the data for which we either already have PC compressed products or will have in the future. The numbers you see are the number of channels in each spectral band, together with the number of PC scores we want to use to represent them. So since the beginning, and we will also always do that, we compress each spectral band independently of the other spectral bands. This is mainly for practical reason, so it leads to a faster compression and a faster reconstruction of the radiances. And also, if there is an instrument failure or degradation in one band, it does not affect the reconstruction of the other bands. But of course, doing it like that, we cannot exploit the interband correlation. So we end up with a lower compression rate than we would otherwise be able to achieve. So in this slide, I introduce some terminology and also make the point that we work always with noise normalized radiances. And this is because with the noise normalized radiances, we ensure that the noise gets evenly distributed over all the eigenvalues, so we can achieve a better separation of the noise and the signal. So the covariance matrix is computed from a large training set of measured spectra, and we noise normalize this covariance, and then we do an eigenvector decomposition. So the eigenvectors that you get from that forms an alternative basis of your measurement space, and the corresponding eigenvalues shows you how much variance you have along these basis directions. So you have a plot here on the right where the blue curves tell you the amount of variance along the different directions, and the red curve is the corresponding amount of noise that you will have, provided that let's say that we have had a perfect characterization of the noise. So you see that only here in the left part, for a relatively small number of the eigenvectors, we have a variance which is actually higher than the variance which is expected by pure noise. So if we select only these eigenvectors, we come up with the matrix A, which we use then for the compression, which consists of two steps. So we have the noise normalization steps, and then we apply the eigenvectors. And if we combine these two into one operation, or in other words, to one matrix, we get what we have called the compression operator. And likewise, to reconstruct the radiances again, we pre-compute the reconstruction operator by pre-multiplying these two matrices. And of course, if you combine the two steps, the compression and the reconstruction, into one, we end up with a projection, and the associated projection matrix we call A. And so this is really a projection which you can verify very easily. So it means that if you apply it twice, you get the same result back. Okay, so now we have an alternative basis. So let's look at how the data looks in this basis. But first, here we look how the data looks in the standard basis. The standard basis is, of course, just the usual channels. And to get the full spectra, you have to sum up all the channels. And the point I want to make here is that all the channels contribute to the atmospheric information. If we would leave out any single channels of here, we would actually lose information. So this is different now if we go to the PC basis. Here again, if you want to get your exact initial spectra back, you would have to sum up all the PC scores to the very end. But here, the information is not really spread over all the PC scores, but it's confined to the leading ones. And we have an example of this. We have here the PC score number 91, and I hope you can see it looks different than the others. The variance is very low. The variance is basically what you would, more or less what you would expect from pure noise. So we have clearly the signal to noise ratio here is way below 1, and you can also appreciate that there's no spatial correlation. So you can also not gain any information from this PC scores, even if you would do spatially averaging. So with the PC scores, you can leave out the majority of the PC scores, and still unlike with the channels, you will not lose any information. So this is a quite basic slide. It's kind of summarized what we do with the spectra. Of course, when we project the original radiances down to the signal space, we end up with two parts: the reconstructed radiance and the residual, which is what we throw away. But you can also think about the radiances as consisting of a real true signal plus another part, which is the random instruments noise. So if you combine these two splits, we can really write each spectrum as a sum of 4 parts, which I have summarized here in this table. So if we look at the reconstructed radiances, it contains the reconstructed signal, of course, which is what we want to keep, but it also contains the noise along the directions in the signal space. So unfortunately, there's no way we can remove the noise within in this signal space. Now, if we look at the residual, well, it also has 2 parts, of course, a part coming from the signal and a part coming from the noise. The part coming from the noise, that's good that we throw it away. That's what we want. This is how we get the compression. But of course, it's possible that a part of the signal could end up in the residual. And if this happens, the term we use for it is reconstruction error. And this is, of course, what we want to avoid. And it's very easy to check in the statistics that normally don't have any signs of signal in the residuals. We can plot maps of the residual, we can look at the histograms, we can make daily statistics. We can see that they behave exactly as we expect from the pure noise, or rather the pure noise that falls into the orthogonal complement of the signal space, to be precise. However, there can be some very, very rare situations where there could be spectra which doesn't fit into the normal statistics of the data. And to identify such spectra, we have introduced what we call the reconstruction score, which is basically just a measure of the size of the residual. And because the residual really is mainly composed of noise, and the noise is not the same for all detectors, and it's also, the noise is also increasing with the increase of the signal. In order to introduce a flagging based on this reconstruction score, we have to take these things into account in order to see what is, let's say, a reconstruction score which is higher than what we would expect from the noise. And this kind of flagging we use to identify outliers. And sometimes there can be some rare events like fires or volcanic eruptions where we might observe some very unusual spectra which are not fully represented by the PC scores. And of course, we use the reconstruction scores to detect such cases. Now, if this happens, so we might want to update our PC bases such that similar features can be represented in the future. For the current PC bases, this was actually quite easy. We just added the spectra, the outlier spectra that we had identified to the training set and recomputed the eigenvectors. And that worked very well. Now I mean, these cases for the Kasatoshi eruption and the Russian fires are now captured very well with the current PC basis. But for the future generation of eigenvectors, we plan to increase the size of the training set to hundreds of millions of spectra. And there, just adding a few spectra in the computation of the covariance matrix might not be enough to get this signal through. But then, I mean, we have other ways of ensuring that we can retain such kind of rare signals, but that's out of the scope of this presentation. Now, sometimes outliers are also caused by instrument anomalies, and actually this is most of the outliers which are detected are actually caused by instrument anomalies, and in this way we can really use this flagging to detect some bad quality spectra which were not flagged in the level 1 processing. So I will not go into the detail of the different cases I have here. Yeah, so now we turn to the reconstructed radiances and the noise characteristics. So just like the original radiances are split in two, I mean, we can easily compute what this means for the noise, which is also split into two. And so we here, I mean, here it's just illustrated with a small part of the spectrum. But what we noticed here, we have the total noise and then the reconstructed noise and plus the noise that we throw out. We noticed two things. One is that the noise is much lower than before if you look at the scale on the color bar, but also that there is some correlations here if you look at this in channel space. So what you might ask, what is the implication of this? And especially if you are still using an optimal estimation or similar approach, where the observation error is an important part. You might ask, so now I have a different noise, and it's smaller. So it seems natural that you should change your observation error covariance matrix in your retrievals to reflect this. But by the way, before I give you the answer to this, I just also want to say that, so it's sometimes people say that it's the compression that introduces a correlation. I think it's not a fair way to formulate it, because in a way, I mean, the correlation is there already in the original radiances. You just only observe it when you look at a certain subspace of your radiance space. So it's not really introduced by the compression. In any case, and now I want to give the answer to the question about the observation error covariance matrix. It's only relevant if you use an optimal estimation approach. Well, you have to stop a bit and think about it, because what is really the role of your observation error covariance matrix within an optimal estimation approach? Well, it appears in the cost function. So it's there to give you a penalty. A penalty for what? A penalty for differences between the observation vector and a forward model simulation. Now, when you and the role of the error covariance matrix is to give weights. If you have a diagonal matrix, I mean, you have separate weights for the differences within each channel. If you have a full matrix, you have separate weights along the eigenvectors of your error covariance matrix. So if you think about it, what you do when you reconstruct is that you remove some directions from your measurements. And when you remove something from a measurement, there's no reason to put a higher penalty for differences along this direction, because these differences can only come now from the forward model, because we did not remove these directions from the forward model. So therefore, if you actually go ahead and do what seems natural at first, you might end up saturating the errors introduced, amplifying the errors introduced by the forward model errors. So you should be very careful here and not just change your observation error matrix without thinking well about it. Well, actually, you shouldn't do it at all. Okay, so what is the impact of switching from original to reconstructed radiance? Well, often you will see a reduction of your retrieval noise, and we have a simple example here with ammonia. But this reduction in the retrieval noise, this is especially true for retrievals or cloud tests which just use a few channels. So in such cases, it's almost a crime to use the original radiances. But so on the other hand, if you're already using a large number of channels, typically you will not have any benefit of switching to reconstructed radiances in terms of retrieval noise. But you might very well be able to speed up your retrievals considerably. For example, so I have seen people running optimal estimation with all or almost all IASI channels. And while you cannot really get better results if you then replace the original channels by reconstructed radiance, of course, doing so is a very inefficient ways to to get the noise reduction which you can get from the reconstructed radiances. Okay, changes is a part of life and should not be feared. And why? I mean, sometimes it can be desirable to update the PC basis. We already seen that we might want to do it to capture some new features that were not included in the original basis set. And there can also be, I will show that short in the next slide, some reason to update the PC basis because of long-term trends in the atmosphere. But such a PC base update that should be viewed, because it's a pure technical change. And you have to remember the important characteristics of the PC basis is the subspace it spans, not its individual vectors. And you shouldn't make any assumptions about particular PC scores behaving in a particular way. What is important is the information which is carried by the PC scores. And this is not going to change much when there is an update of the PC basis. And I think I have time to explain. So the figures to the right. So this shows some statistics of the differences which will be introduced by switching from one set of PCs to another set of PCs. So version 1.4 is the current PC basis, and what I've called here 2.1 is a PC basis which I'm preparing, and it will become operational sometimes next year. And I mean it's very different in many aspects from the current one. The current one was last updated in 2011, so of course it has no information from specs newer than that. And we have a different way of treating the mean in the new one, and we have a full matrix noise normalization before we just have a diagonal. There are several differences in the two set of eigenvectors. Yet you see here, if you zoom in very much in your plot, you basically cannot spot the differences in the reconstructed radiances coming from the two different sets of eigenvectors. And this is also, I mean, this is confirmed statistically. So the mean difference between the two sets of reconstructed radians is close to 0, and the standard deviation is very low. So there's absolutely no fear well, no reason to fear a PC basis update. Now, I promised to talk shortly about the atmospheric trends. I mean, we know that we see a gradual decrease of CFC12 in the atmosphere, and at the same time the SF6 is increasing, and this we can actually see in the mean of the residuals. So there is a slide for some channels which responds to these gases. There is a slight small bias in the residuals, which is increasing from year to year. So, I mean, this is another example. If you want to get rid of these biases, we will have to update the eigenvectors. But of course, if you don't do it, another way to capture these trends in the atmosphere is also using the hybrid PC methods, which I will introduce in the next slide. So we have seen already that the PC compression with static eigenvectors based on a big global set of observed radiances works very well in the vast majority of situations. But there can be some some very exceptional situations, like for example the Calbuco eruptions, where there is some features which are not captured by the static global eigenvectors. And of course, I mean, we could get rid of this problem by just, instead of using global eigenvectors for each new granule of data, we could compute new eigenvectors just for the current granule of data being disseminated. That would solve that problem. But it turns out that besides retaining more noise, even worse, it will, using just local eigenvectors, we would actually retain less atmospheric signals. So this is definitely not a good idea. But instead, we combine the best of the two worlds. So we just complement our PC scores, which are based on global eigenvectors, with a few supplemental directions which are computed locally for the granule which is being compressed. And so to conclude, I have here a slide with 3 different compressed representations of the radiances. I've mainly in my talk, I've mainly been focusing on the reconstructed radiances, which really represent the same physical quantities as the original radiances and can be used in the same way. So if you're interested, if you want to understand how your particular retrieval will react to a change to reconstructed radiances, it's very useful to look at the so-called gain matrix, which is the derivative of your retrieval with respect to the radiances. So if, for example, if you compute, then you can do that. I mean, of course, you can do that for a couple of different situations. But if you compute now this matrix, so G times A minus A, you will get an indication of how sensitive your retrieval is to directions which are orthogonal to the signal space. In other words, how sensitive is your retrieval to noise. And you can also use then, I mean, you can also compute the expected improvement in the retrieval noise. Now, PC scores, of course, this is the representation we use for the dissemination. But also, I mean, I expect that by the time that the IASI-NG and IRS are flying, most applications will be based on machine learning, and PC scores is kind of the standard representation of your measurements for machine learning applications. But I mean, you don't need, of course, you don't need to use the PC basis, which is used for dissemination. In fact, you should use a fixed basis such that you are not, I mean, such that you are not affected when the PC basis is updated. And of course, it's very easy to go directly from one compressed representation to another compressed representation. You just have to pre-compute the two corresponding matrices, and there you go. And then finally, although I have not really talked, it's a bit outside the scope of the rest of the presentation, but especially if you are using the data for a simulation. So there is another way to represent the information in the data in a compressed way, and that's as PC scores of the level 2 profiles. And we can set up these PC scores in a way such that they only represent the broad scale features of the level 2 programs, the features which can actually be observed by the instrument. And by doing that, we avoid making any assumptions about the structure of the profiles within the null space. And so we avoid the problem which historically led to the level 2 assimilation being abandoned. And of course, we also avoid the problems of level 2 assimilation. I mean, maybe you think there's no problems with level 1 assimilation, but for sure, I mean, it uses the forward model as observation operator, and besides being slow, while it has the advantages that it really requires that you have access to all the relevant input parameters to your forward model in order to be able to apply it. And typically, not all these parameters are part of your model. So we think that this representation is a very promising way to use the data for assimilation purposes. And we're currently conducting a study together with ECMWF to kind of prove the concept and to look at the practical aspects of it. And with this, I open the floor for questions.
Thank you, Tim, for this talk. And there is a number of questions in the Slido already. Let's see. Before we get to those, one question from me. When the eigenvectors and the PC basis is changed, will the old version still be available to users if they want to compare the effects and what you talked about with using the gain matrix on their retrievals?
Yes, definitely.
That's in the archive then?
Yes, they are in the archive, and we also have them. Since we really have only in the history of IASI, we have really only had 2 different sets. So they are also both available from EUMETSAT web pages, but also in the archive.
Right. Okay, let's pick the first one here. Are the selected eigenvectors of the local PC basis going to be disseminated with the same timeliness as level 1B data?
Okay, I'm afraid I don't know exactly the answer to this. Maybe somebody can help.
Well, level 1B data, the spectra will only be available for IASI-NG and through one of the EUMETCAS services, the spectra. So the PCs will also be made available in near real time.
Oh, sorry. Okay. Well, now, sorry. I was a bit confused by the question. So we're talking about the hybrid, the local PCs for the hybrid. Yes, they are, of course, disseminate together with the rest of the compressed products.
So the answer is yes. Okay, next question. There is a question here. Any software for reconstructing radiances from the PCs, which works for any user, will be made available?
Well, well, it could be, but traditional. I mean, EUMETSAT has not really been willing to make software available, but I don't know if that will change in the future.
Okay, we can keep it that way as a question that we will document all questions. We'll try to answer as many as we can now, and the others will answer them offline after the after this event, and we'll address that one too. There's an interesting question here. There are many ways to use the data besides optimal estimation and without the use of forward models. How should we document the noise of the reconstructed radiances?
Well, I agree there are many ways to use the data, and so I think I also touched about it. I think most users of the data will be with machine learning, and you don't actually need to have you don't need to know the noise in the data when you're applying machine learning. But I mean, if you want, I mean, it's just as also shown in maybe I can put this slide up. I mean, it's very easy to compute. Here you see the formula. If you know the noise in the original.
Can you share your screen again?
So yeah. Okay. So yeah, so this is yeah. Well, this just show how you can get to the instrument noise within the reconstructed radiances. So, but I mean, it's normally not really interesting if you're not using optimal estimation. Well, even if in optimal estimation, this is just a minor part of the observation error, so it's not really interesting for optimal estimation either.
Okay, thanks, Tim. Yeah, there was information here about the SAFs. These are the EUMETSAT satellite application facilities, which are consortia which contribute software and products based on EUMETSAT data. And as we heard also before, there are plans by the SAF for numerical weather prediction and the SAF for nowcasting to provide software to be able to reconstruct radiances for IRS. Okay, there was a question here, the second one. Have you considered nonlinear dimensionality reduction methods besides the principal component analysis?
No, we have not.
Next question, is the assimilation of PCs of level 2 profiles equivalent to assimilation of transformed retrieval scale projected states?
Yes, you could say so. It's I mean the concept is very similar. I mean, you instead of using, let's say, 100 levels to represent a profile, you use a small number of values to represent the profile. So, and this way you don't need to represent what you cannot measure. So I mean, whether you can say it's equivalent, maybe it's a big word, but I mean, it's very similar, yes.
Okay, there's again a question about the way to obtain reconstructed radiances from the PCs.
Yes, I think, I mean, you apply, and basically it's just a multiplication. So your PCs is a vector, and then you have a matrix, which is, I showed in one of the slides, the reconstruction operator. So the dimension of the reconstruction operator is the number of channels in one direction and the number of PC scores in the other direction. And you just multiply this matrix with your PC scores and you get the reconstructed radiances. So that's very easy.
All right, thanks very much, Tim. I don't see any further questions in Slido. Yes, again, thank you very much for this. So there is a plan by the nowcasting satellite application facility to provide software which enables this reconstruction for MTG IRS. Okay, dear participants, we still have plenty of time for answering your questions. I think there's a question about the matrices that you use. So this is the noise normalization matrix, I think.
Yeah. Yeah, well, okay, well, it's well, SY it's just let's say the instrument noise, but so but what is available in the eigenvector files is the noise normalization matrix, which is just the matrix square root of SY. So in that sense, SY is available, and A, of course, A is the product. What we also, I mean, both the compression operator and the reconstruction operators can be computed just from the noise normalization matrix and the eigenvectors. But for convenience, we also pre-compute them such that we get the reconstruction operator and the compression operator, and we put them into the eigenvector files. Now A will just A will be bigger, right? Because the dimension of A is the number of channels time number of channels. So it's a bit wasteful to put that in the files which will be sent out to everybody. So, but you just multiply your compression operator and your reconstructors operator, and voila, you have A. So in that sense, it's also available.
Okay, Tim. And if there aren't any more questions, well, you can still have a couple of minutes to post your questions while I'm starting to summarize the event. So we've today in this first user preparation webinar focused on the next generation hyperspectral infrared sounders with details on the instruments, the measurements, the data and their format and dissemination, and the level 1 data, in particular the way principal components will be used. And we are very grateful for such a big audience, also from outside Europe, and thanks also for any participants from Asia for staying up so late today, as well as for participants from the Americas who have joined us. If you have any questions, please post them on Slido. It'll remain open until tomorrow. So we'll have tomorrow another slot of 2 hours to discuss more the geophysical products and indicate some of the applications, mostly for nowcasting, NWP, and atmospheric composition that we expect to benefit from these new data streams. And I also would like to remind you to give us 1 minute of your time after this event to answer the questions in our little poll. In EUMETSAT, we're planning a whole series of these user preparation webinars, focusing also on the other observation missions. So we'd like to know what you liked about this event and maybe what we could improve next time. There is another question, yeah, from on Slido. Yes, we still have a bit of time. Yeah, thanks for that. So we will use PC-RT-TOF. I assume PC-RT-TOF is based on RT-TOF simulation instead of observations. Can we use PC-RT-TOF as it is for the PCs coming from EUMETSAT?
No, because I mean that's other bases. I mean, well, okay, you can use PC-RT-TOF as it is. Yes, that you can, of course, but you cannot. I mean, the PCs that will be simulated are not the same as the PCs that will be disseminated. So you have to make the transformation, but you don't have to go via the reconstructed radiances, right? You can go directly from the PC scores which are disseminated to the PC scores which are generated by PC-RT-TOF. So in that way, I mean, PC-RT-TOF itself, yes, you can definitely use as it is.
Okay. All right, so yes, thanks for that, Tim. I should have mentioned that for the event tomorrow, you need to register separately. So please go to the links that were made available via various channels and register for tomorrow's slot. So the meeting slot today is not valid tomorrow. There's a couple of comments here, so I'll leave this on the slide. I would like to thank the speakers from EUMETSAT for their engagement and for their time to prepare these presentations and to answer the questions. As I said, we will look at your questions after this event and answer them offline and make the material available along with the presentations and the recording. The poll is now active in Slido, so please please answer it. And with that, if there are no further comments or questions, I would like to close the meeting. So thank you very much for your attention today, and I'll close the meeting now.